So let us consider the network. In this network, the branches having voltage source V1 and another branch having the resistor R1 and inductor L2 and capacitor C3, and next one is R4 connected in series with the voltage source V2. So we will discuss about four elements here. What is meant by node, junction, branch and loop. Node means a point at which two or more elements are joined together. That point is called as node. For example, the branch containing voltage source V1 and another branch containing resistor R1 are connected at this point. So because of this reason, A acts as a node. Similarly, coming to B here, B is also example of node here in this network because the branch containing resistor R1 is connected at this point with the inductor L2. Hence, likewise, C is also node, D is also node, E is also node, F is also node. So in this network, total A, B, C, D, E, and F. These many nodes are there. Next, we move on to the next topic, that is junction. What is meant by junction? A point at which three or more circuit elements are joined together is called as junction. So there is a difference between node and junction. Coming to the node, only two, minimum two, maximum more. But coming to junction, minimum is three. A point at which three or more circuit elements are joined together is called as junction. So for this definition, as per this definition, now let's see which are the points that are going to act as a junction. A acts as a junction? No, because only two elements are connected. As per the definition of junction, minimum three. So let us move on to the B. See, for this point, B point, uh, element R1 is connected, element L2 is connected, element C3 is connected. Hence, B acts as a junction. Now, let us move on to the C. Whether C acts as a junction? No, because for this point, only two elements are connected. So, leave it. Coming to D, D acts as an element? No, because only two circuit elements are connected. Leave it. Coming to E, in this point, see, this branch is connected and this branch is connected and this branch is connected. So hence E is also acts as a junction. So in this network, total two junctions are there, that is B and E. What is meant by branch? A part of the network which connects the various points of the network with one another is called as a branch. I will repeat. In a network, a part of the network which connects the various points of the network with one another is called as a branch. So in this figure, AB acts as a branch, BC acts as a branch, CD acts as a branch, similarly ED, FEF. So a part of the network which connects various points, A is connected with B, so it acts as a AB acts as a branch. B is connected with C. The capacitor one end is connected to B, capacitor other end is connected to C, so it acts as a branch. Loop. What is meant by loop? Loop is a set of branches forming a closed path in a network, that is called as a loop. Loop means what? It is the set of branches. 1, 2, 3, 4, 5, 6. Total how many branches are there? 1, 2, 3, 4, 5, 6, 7. 7 branches are there in this network. It is a set of branches forming a closed path, that is called as a loop. So in this network, we will give the examples for the loop as first one is A, B, E, F. Starting with A and move on to B, then E, F. This is the closed path. One example, and end with A. A, B, E, F, A. Similarly, we can say B, C, D, E, B. It is the second example of loop. One loop, second loop. We'll take the outer loop, that is A, B, C, D, E, F, A. It is the example of what? Outer loop. So this is about the basic concepts of node, junction, branch, and loop. So next topic is we'll see Cramer's rule. Uh, this rule is very helpful for solving the given network. If the network is said to be complex one, then we are making use of this rule. Okay. If the network is complex, or the number of equations, that is unknowns, are more than it is in the more number of equations, more number of unknowns are present in the given equation, given network. In such cases, the solution of simultaneous equations can be obtained by using Cramer's rules. So how we are going to make use of this rule for solving the complex network? See, with an example we will see. I am going to represent unknowns x1, x2, x3, so on, xn. X1 to xn, these are the unknowns. So how many unknowns are there? N unknowns are there in this equation with coefficients a11 x1 plus a12 x1, sorry x2, then a13 x3 plus so on a1n xn is equal to c1, where c1 is a constant term. Similarly, second same equation, in that case, the coefficient of x1 is a21, coefficient of x2 is a22. Similarly, second equation is written. So on, if you are writing nth equation, an1 x1 plus an2 x2 plus an3 x3, so on, ann xn equal to cn. So in each equation, there are n unknowns, x1, x2, x3, xn. Similarly, these type of equations we are getting how many? Total C1, C2, C3, so on up to Cn. So n unknowns are there. These kind of equations we are getting n equations. If it is so, then how to find these unknowns x1, x2, x3 up to xn? So for that, we have to follow the Cramer's rule. Cramer's rule means first we have to find the determinant of the given equation. How to find? I'm going to represent the determinant as a delta. Delta equal to the coefficient of x1 is a11, the coefficient of x2 is a12. Similarly, the coefficient of xn is a1n. Similarly, coming to the second equation, the coefficient of x1 is a21, x2 is a22, so on, xn is a2n. Similarly, last equation, the coefficient of x1 is an1, an2, ann. So I written all the coefficients. In each equations there are n unknowns, there are n equations. So I written the coefficients of x1 to xn. Then I have to find the determinant for this one. Already we discussed, maybe you discussed in the mathematics subject how to find the determinants. So using the same concept, we have to find the determinant for the given this matrix. We can represent the determinant as delta, or we can represent it as a d. So how to find these unknowns x1, x2, x3, x4, so on up to xn? So in order to find x1, so first we have to find the subdeterminants. D1 indicates the determinant of x1, D2 indicates the determinant of x2, D3 indicates the determinant of x3. Similarly, Dn indicates the determinant of xn. So how to find determinant 1? Sub these determinants. In order to find subdeterminants, the respective columns are replaced by the constant terms. Say for example, if we are finding the unknown x1, one stands for first column. So first columns are replaced by the constant terms c1, c2, c3, so on up to cn. Similarly, if you are calculating x2, the respective determinant is d2. So 2 means second column. Second column coefficients are replaced by constant terms c1, c2, c3, so on, cn. Similarly, we want to calculate xn. The coefficient term is nothing but the respective determinant is dn. So nth column is replaced by c1, c2, c3, so on, cn. So D1, D2, D3, D4, so on, Dn are the respective determinants, subdeterminants. Next, after calculating these subdeterminants, we have to find unknowns as, say for example, we have to calculate x1, then that is equal to subdeterminant 1 divided by main determinant d1 by d. Second unknown x2 equal to d2 by d, x3 equal to d3 by d, x4 equal to d4 by d, so on, xn equal to dn by d. It is about calculation of unknowns if there is a complex network or if there are unknowns are more. Okay. Next we will discuss source transformation. Source transformation, the name itself indicates transforming one source to another source. transforming one source to another source means one energy source is converted into an equivalent energy source. We know there are two energy sources, that is voltage source and current source. Then how to convert voltage source to current source and current source to voltage source, we are going to discuss in this topic under this title. Uh, so why we are doing this source transformation means the why we have to study this source transformation means the need of source transformation is sometimes in the complex network both the energy sources may be present. Both the energy sources means voltage source and current sources are present. But in loop but in loop analysis, all the energy sources should be preferably voltage sources, and in node analysis, all the energy sources should be preferably current sources. So the source transformation technique is useful in converting voltage source to current source and current source to voltage source. I will repeat. Uh, in loop analysis, all the energy sources should be voltage source, and in nodal analysis, all the energy sources should be current sources. But in sometimes it is the combination of these two sources, voltage source as well as current source. At that time, we are making use of source transformation technique. Source transformation technique means converting voltage source to current source and vice versa. So the replacement of particular energy source by an equivalent source is called as source transformation. Okay. To perform source transformation, the following conditions must be satisfied. Okay. We have to follow these 2 points. First, the open circuit voltages at their terminals must be equal. Second point, the short circuit current at their terminals must be equal. Okay, 2 points we have to remember. First point is open circuit voltages at their terminals must be equal. First point, voltages at their terminals must be equal. Similarly, short circuit current at their terminals must be equal. These 2 points we have to remember. So let us consider two circuits. I'm going to consider two circuits here. First circuit is indicated nothing but it is the voltage source, because voltage source is connected in series with the resistance. Okay, the voltage source is represented by Vs, and this is connected in series with the resistor Rs. Through this circuit, the current, terminal current, IT stands for terminal current. IT is flowing. Okay, and these two terminals, across these two terminals, terminal voltage is represented as a Vt. Similarly, I consider another circuit, that is current source circuit. Current source is represented as Is, and this current source Is is connected in parallel with resistor Rs. Through this uh, terminal current is represented as It, and terminal voltage is represented by Vt. Vt stands for terminal voltage. Okay. Now, how we are converting this voltage source to current source and vice versa, we will discuss. First, I will consider this network voltage source. For this voltage source, how much voltage is present across this terminal? Supply voltage, Vs stands for supply voltage. We are giving this amount of supply voltage to the network, and to this supply voltage we connected one resistor in series. Because of this reason, there is a drop. There is a drop in the voltage. But how much voltage drop across these terminals? That is terminal voltage is nothing but the voltage across this end, across these two terminals, is represented as Vt. Vt equal to Vs. Vt equal to Vs minus current flowing through the resistor, that is It into Rs. So Vt equal to terminal voltage across these two terminals is calculated as supply voltage minus drop. Vt equal to Vs minus It into Rs. Okay. Similarly, rearrange the terms. We want It, so I am going to rearrange the terms. So It into Rs equal to Vs minus Vt. I rearrange the terms. Then It equal to what? For the simplification, I will take Rs towards the RHS. So Vs minus Vt divided by Rs. Separate the terms. It equal to Vs by Rs minus Vt by Rs. Okay. I am going to represent it as equation number 1. So similarly for the current source, second network consider. at node A, Is equal to It plus Vt by Rs. Okay, already we calculated It here. It equal to what? Vs by Rs minus Vt by Rs. So let us compare these two equations. Let us compare these two equations and what we are getting. So first I calculated Is equal to It plus Vt by Rs. Then I rearrange the terms. I have taken It because we have to express in terms of terminal current. So I have taken It here, then Is here. It becomes Is minus Vt by Rs. So compare equation 1 and 2. What we are getting? Is equal to Vs by Rs. Same thing. So supply voltage equal to what? Supply current equal to what? Supply voltage divided by resistance. This is about what? Source transformation technique. So this voltage source is transformed to current source. Simple thing. Always voltage sources are connected in series with resistance and current sources are connected in parallel with the resistance. Okay, we will discuss with help of an example. Reduce the below circuit to a voltage source in series with resistance between terminals A and B. Reduce the below circuit to a voltage source in series with resistance between terminals A and B. So the network is given with the terminals A and B. In between these two terminals, so many branches are there, so many circuit elements are there, so many energy sources are there. See here, one energy source, second, third, fourth, fifth. So in between these two terminals A and B, total 5 energy sources are there and some other branches are there, but we have to what? We have to reduce the below network to a voltage source in series with resistance. So we have to reduce this network in such a way that finally in between these two terminals A and B, we have to get only one voltage source, that too in series with resistance. Likewise, we have to reduce. So we have to reduce this network with the help of source transformation technique. First step, see here, voltage source is there in for this voltage source there is no connection, but current source is connected in parallel with the resistance. So I am going to convert this current source to voltage source. So converting this current to voltage, we have to express this as a in terms of voltage. Means what? V equal to I into R. I is how much? 2 ampere. R is how much? 5 ohm. Hence 2 into 5, 10 ohm. So sorry, what? 10 volt. So 10 volt is connected in series with 5 ohm resistance. But observe the polarity of representing the voltage source. We have to represent the polarity of the voltage source after converting current source to voltage source based on the arrow mark. The arrow mark at is pointing towards left side. So like this. So left side plus, right side minus. Tail of the arrow mark is minus, head of the arrow mark is plus. I will repeat. Head of the arrow mark is represented as a plus, tail of the arrow mark is represented as a minus. So how we converted? V equal to I into R. I is 2, R is 5. So 2 into 5, 10, 10 volt. That is in series with the 5 ohm. Now in this branch, there are two voltage sources. Observe the polarity. These two voltages having different polarity. Okay, these two voltage sources having different polarity. So this is plus minus, minus plus. So 10 minus 5, that is 5 volt we are getting. 5 volt we are going to getting. Then this 5 volt I am going to represent in terms of current source. I equal to what? V by R. V is how much? 5 volt. R is how much? 5. So 5 by 5, I am getting 1 ampere current. So what about the representation of arrow mark? So this is after simplifying these two voltage sources. After simplifying these two voltage sources, I am getting like this: plus minus 5 volt. I am getting like this. So this is converted to current source. Current equal to what? I equal to V by R. So that is 5 by 5. That is 1 ampere I am getting. 1 ampere means, observe the arrow mark, plus is there. Because of that reason, always I told arrow mark head is representing plus, tail is representing minus. Hence we are writing like this. So 1 ampere in parallel with 5 ohm resistance. Coming to second branch, once again I am converting this a voltage source in series with resistance as a current source in parallel with resistance. So if you are converting this 9 volt to current source, so I equal to what? V by R. So 9 by 3 means 3 amperes. So observe the arrow mark, plus is present here, so the arrow mark head is like this, tail is minus, that is in parallel with 3 ohm resistance. Next, there is no change in the this branch because here also current source is present. Last one is also current source is present. Next, here 1, 2, 3, 4. There are 4 current sources are present, but having different direction. So let us simplify by adding. So one is moving left side, and 3 is moving right side, and 2 is moving left side, 6 is moving right side. Maximum value is 6. So I will consider this one as a reference. So 6 and minus 2, 4, plus 3, 7, minus 1, 6. So how much you're getting? 6 amperes. Or we can write like this. One more steps we can make use of this one. I'm re-sketching this network as left side arrow mark represents downwards and right side arrow mark represents upwards. Repeat, I will repeat. Left side representation of arrow mark represents downwards, right side represents upwards. So this one I am resketching. 1 ampere is left side means downwards, and 3 ampere is right side means upwards. 2 ampere is left side means downwards. 6 ampere is right side means upwards. Those are connected in parallel with some resistance 5 ohm, in parallel with 3 ohm, parallel with 1 ohm. So let us simplify the resistance in parallel. Resistance 5 ohm, resistance 3 ohm, resistance 1 ohm are in parallel. Equivalent resistance we are going to calculate 1 by R equal to 1 by 5 plus 1 by 3 plus 1 by 1. Further simplifying, we are getting the answer as 23 by 15. 1 by R equivalent equal to 23 by 15. But R equivalent equal to reciprocal, that is 15 by 23. So all these currents are connected in parallel with simplified equivalent resistance 15 by 23. Now simplified. So as I told, I will take the above maximum value is 6 as a plus. So 6 is what? 6. So downwards means minus, upwards means up, plus. So minus 1, plus 3, minus 2, plus 6. Downward current I taken as a minus, upward current I taken as a plus. So it is downward minus 1, it is upward plus 3, 2 ampere is a downward minus 2, 6 ampere is a upward, so plus 6. That is equal to, simplify, we will get 6 amperes. Hence 6 ampere current is in parallel with 15 by 23 resistance. But what is asking for? Reduce the network in such a way that the finally that in between terminals A and B there should be a one voltage source in series with resistance. But we got what? In between the terminals A and B we got a current source in parallel with resistance. Let us convert this current source to voltage source. V equal to what? V equal to I into R. Hence 6 multiplied by 15 by 23. So what we are getting? 6 into 15, that is 90. 90 by 23 volt. That is in series with 15 by 23 resistance. So finally we got in between the terminals A and B, we got a voltage source having the value 90 by 23 volt in series with the resistance 15 by 23. This is about the source transformation.